Hello, everybody. Happy Monday. Today we are starting chapter 6, which is our sensations and perceptions unit. Now, this unit, at least for me, I'm pretty bummed that we can't be in person specifically for this one because there's a lot of different activities that we do with vision, perception goggles, and kinesthetic bodily stuff that I think is really fun. But I'm going to try and get you looking at some of the optical illusions and ways our brain interprets the information that it's receiving and actually makes sense of it in regards to our vision and other senses. So that's what we're starting today. Today's lecture is really just an intro into sensation and perception. What are the ideas that this is relating to? We're going to look at a lot of optical illusions, which is always fun. There's videos to kind of break down optical illusions and, again, why our brain is interpreting certain images in the way that it does. Tomorrow, you're going to watch a lecture on vision, so the actual biology of an eye and how it takes in light rays and then flips them around, does a little bibbity bobbity boo, and we see a dog or a water bottle or whatever. You will also be introduced to monocular, binocular, and gestalt principle cues on how we perceive depth perception, how we perceive where things are in relation to us, which is going to get you started then on your activity for Wednesday, which is actually going out into the world, aka outside, and taking pictures and videos that reiterate or give examples of those different principles. Thursday then is hearing and the other senses, and then your FRQ is on Friday. So that's kind of the plan for today. This week, I guess. I will say that the scavenger hunt, the photography scavenger hunt that you're doing on Wednesday may take a little bit more time than some of the other independent study things. It may or may not. It totally depends on you and how quick you are at kind of distinguishing those different perceptual cues. So it might be something worth starting on Tuesday after you watch the lecture and then finishing up on Wednesday, but you guys can kind of figure out how that's all going to work. So with that, I introduce you to sensations and perceptions. So let's go ahead and get started right away with our intro to sensations and perceptions. I'm going to start by just looking at what are the differences between sensation and perception. Intuitively, a sensation is the process by which our sensory receptors and nervous system receive and represent stimulus energies from our environment, right? That's a pretty long-handed way of saying what are you actually taking in, right? How does our body see things? How does our body hear things? What is the actual stimulus that's coming from our environment, right? The brain receives input from the sensory organs. If you touch a hot stove, your finger says, ouch, hot, right? If somebody drops a textbook 2 desks down, right, your brain goes, whoa, sound, right? That's a sensation. Perception then is tying meaning to that sensation, right? The perception is the process of organizing and interpreting sensory information, enabling us to recognize meaningful objects and events, right? This is when our brain is making sense out of the input from sensory organs, right? So when we attach meaning to those sounds, right, instead of the textbook dropping and our brain saying oh, that was a loud noise, we say, I'm at school, we're working with textbooks, somebody dropped their textbook, right? So we have sensation and we have perception. We're going to look, just kind of start this conversation by watching a quick video of a kid named Ben Underwood, who has been blind since he was very, very young, and he has learned to use his ears and his auditory system to actually see the world around him by using echoes and sonic. You'll see, the video will explain it, but it's pretty cool, and it gives us some insight into what is that sensation and perception and how do our brains actually work and interpret the world around us.
Ben Underwood is blind. Both eyes were removed when he was 3, leaving him with no vision at all. So how on earth does Ben do this? And this? And even this?
I don't think I've ever come across somebody like Ben. You know, he was quite unique.
Ben lost his eyes to cancer, but unbelievably, he's taught himself to see with sound.
If he chooses to go out there and ride that bicycle, let him ride the bicycle.
It's got to be very smart. Somewhere in there, it's a little genius going on.
I don't consider myself blind. Ain't nothing wrong with me.
Ben has no guide dog and never uses a white cane. He's not even using his hands. Instead, he sees with sound. He makes a sharp click which bounces back off nearby objects. Amazingly, Ben's ears pick up the echoes and he can precisely locate where things are. Ben is the only person in the world who sees using nothing but echolocation.
Well, I've been able to tell where walls are and where things on the ground are. If I click down, then I can hear them easier. But if I'm walking, I'm just clicking over it, it's not gonna get it. And I can tell where desks are in the classroom and stuff like that. I can hear the wall over there, the couch over there. I can hear the wall behind me. I can hear the wall over there and the TV and the computer. Yep.
Ben, I need a towel for drying because I don't have all my kitchen towels in here. All right, Mom, I'm going to go get it.
Ben's echolocation is so good that at home his mum, Aquanetta, Uncle Kerry, and brother Isaiah make no allowances for his blindness at all.
When I was a little kid, I didn't really know he was blind. I just knew he was my brother.
Did he make it? He's determined to do what he's gonna do. And he refuses for somebody to label him as blind. You see this kid that has a whole different way of thinking. It's magic and it's real.
I don't think I've ever seen anyone quite as remarkable as Ben, nor have I seen anyone quite as remarkable as Ben's mom. And I think that's a lot of the secret to Ben's amazing talents.
He knows that there's nothing impossible for him, you know, and it's not.
So obviously this didn't transfer over super well, so I just retyped that bottom-up processing. So we are looking at here kind of the difference between bottom-up and top-down processing. So these are two different ways in which we kind of integrate our sensations and our perceptions, how our brain makes sense of the world around us. I've said that a few times, but bottom-up and top-down processing are very, very important to our understanding of these ideas. So bottom-up processing is taking sensory information and then assembling and integrating it, right? That's this idea of we see something, we actively think about it, and we actively piece the puzzle together to interpret or figure out what's going on. Whereas top-down processing is when we kind of fit experiences or things into schemas or kind of those big grouping characteristics of what we already know, and we fit that information into a pre-existing understanding, right? We're using models, ideas, and expectations to interpret that sensory information, right? So you see something, and from top down, you're gonna assume it's this because you've seen this before. Right now I'm looking at my coffee cup, right? I'm assuming that's a coffee cup because that's what a coffee cup looks like. I don't really have to think a ton about that. It's a cup, I know that. How do I know it's a coffee cup? Well, it has a handle, it's insulated, right, whatever. That would be that top-down processing, whereas bottom-up processing is when we're it's a lot of times when we're interpreting situations for the first time and we have to think about what is actually going on. We assemble that information and really come to a full picture of what's going on in our brains. So bottom-up and top-down. We're going to look at a few examples here. So here is an image, and the question is, what do you see? Take a second, look at it. This image has been used. We know that children actually generally see 8 dolphins. I'll kind of highlight them for you, just so you know, right? 1 dolphin, 2 dolphin, 3, 4, 5, 6, 7, 8, right? So children see 8 dolphins. And oftentimes when adults are looking at this image, they see a nude couple in an embrace, right? And so why do kids and adults see something that is different? Well, it's because of this top-down processing idea, right? It's the idea that children use different experiences and different models to base their assumptions off of, right? They are likely to have seen more dolphins in their life than pictures of nude embraces, right? Whereas adults do more top-down processing, are more likely to see objects that aren't fully there. This shows that seeing involves the process of perception, and it's not just the process of our eye taking in information, right? Sometimes people look at this and they really just see shadows on a bottle. They don't necessarily see the images, right? It takes a little bit of time to maybe see the embrace. It maybe takes a little bit of time to see the dolphins, right? And that's kind of that understanding of our top-down processing and what we see and why we see it. It's because we're basing it on previous experiences. So another example, bottom-up processing. We know that the letter A is really all black blotch seen as separate components by the brain, right? Bottom-up processing would say, I see 3 lines. When they're put together, they create an A, which sounds like ah, if you remember kindergarten. A, ah, right? The analysis of a stimulus begins with the feature detector cells identifying the building blocks or small components sent by sensory receptors. So if we're bottom-up processing something, we're taking in all aspects of it and integrating that into our understanding, right? So when we think about how that is different from top-down, right? Top-down processing occurs when we construct perceptions, drawing on experiences and expectations, right? We've all read a lot. We know what an A looks like. We don't have to interpret the A as 3 different lines and integrate that into our understanding of an A. We just assume it's an A even when it's not fully an A here, right? Like here you see the cat. We assume while the H and the A are the exact same kind of symbol, we've seen the word we've seen the word cat, and so we draw on our previous experiences to be able to differentiate between these 2 symbols. So what do you see here? What does this say? Many of you are probably saying, duh, it says I love psychology, right? This example shows us that our perception of the world is created on both the actual sensory info that we're receiving, right? That's that bottom-up kind of mentality, and our thoughts and our expectations. So here, right, it actually says this. Obviously, it was all in one line on the previous slide, but we made some top-down assumptions based on our previous experiences, based on the understanding that you are in psychology class, and that you've seen these letters before. You can assume that it said, I love psychology. Obviously, it does not. And looking at it now, we're kind of integrating our bottom-up perception ideas by looking at these as individual letters because they don't really make a single word. But we know, again, that idea that our perception of the world is based on both our bottom-up and our top-down interpretations. So one last kind of example before we look at the ultimate example in a video form. But top-down processing, again, another question. What do you see here, right? As you look at this image, you may start to see something in the picture if we give your brain some concepts to apply. Can you see a tree? A sidewalk? A dog? Specifically a Dalmatian? With those cues, you have this preconceived notion of what those things look like, and you're able to apply them to this image, which doesn't really inherently lend itself to an actual image. So right here, you see our tree is kind of over in this area, right? Our sidewalk is kind of walking this way. Looking at the dog, right? We have a Dalmatian right in here. And it's not perfect. And even when I highlight it, it kind of like goes away. It's even harder to see almost when I highlight it. But we are able, our brain is able to use that top-down processing to make some of those inferences. Said the pinnacle of all top-down, bottom-up processing ideas is going to be shown in this hollow face illusion. So I'm going to let you watch it and then we'll talk about it real quick.
The hollow face illusion is one of my all-time favourite optical effects. And we've had an Einstein mask for many years. Now we have one that's fully painted, decorated by an artist. An effect with all the flesh tones and the white hair and so on is remarkable because it really does look like Einstein himself. But this is a hollow face, don't forget. Here is the piece being turned around very slowly to show that it's hollow that side, and then this side is all in grey. You're not supposed to see this side. Normally it's just the back of the mask. We keep turning around, and this nice effect here as he suddenly pops out to you, because although it's a hollow face, he's going to suddenly pop in your imagination to be a full face. An effect like that also, which is very remarkable, is when you tilt the piece back and forward like that, you get some very, very strange effects of the head tilting upwards and downwards, and the eyes seem to follow you up and down. And now if we just leave the mask on the table and move the camera, you'll get some very interesting extra effects as well. Hollow face illusion.
So that's pretty crazy. So obviously this is our brain kind of in conflict with one another. This is an example basically of our top-down thought processes auto-correcting our bottom-up thought processes, saying it's concave, right? Our bottom-up processing is telling us it's concave. We see that it's concave, but our top-down processing is like, no, that's weird. That's just a face. That's just a drawing of a face in 3D, right? It shouldn't be concave because that's not the norm. And so our top-down processing autocorrects for our bottom-up processing. And then obviously as they turn around and you kind of see that, our brain starts to adjust to the understanding that this is in fact a hollow concave face. So that one's crazy. Just a couple of the optical illusions talking top down, bottom up. We have a bunch more to get through, so let's continue on our merry way. So today's intro, we're really just going to focus on sensation. Tomorrow you're talking vision and then the perception piece of things. But when we're talking about sensation, we can see this process as basically 3 steps, right? We have reception, transduction, and transmission. Right? Reception is the stimulation of sensory receptor cells by energy, whether that be sound, light, heat, whatever it might be. That's like our receptor cells taking in some sort of stimulus, right? That's reception. Then we see transduction, which is the transformation of this cell stimulation into neural impulses. So that's like the actual sound coming into our ear and starting kind of that neural impulse, that action potential, the actual like firing of neurons to get to the brain for us to then transmit, or this transmission process which delivers the neural information to the brain to be processed, right? So reception, transduction, and transmission. With that said, there are terms that we need to recognize as it pertains to sensation. And the first one is the absolute threshold. And this refers to the minimum level of stimulus intensity needed to detect a stimulus half the time. So if you've ever I actually think you all have to do this, like at the nurse's office when you have to like listen for a beep in your headphone, or in they have those big old headphones like this picture showing. and they play a beep, and you have to like raise your hand when you hear the beep in each ear, right? That's testing your absolute threshold. Refers to the minimum level of stimulus needed to detect that stimulus half the time. So how loud does a beep need to be for you to be able to actually perceive it and actually recognize it 50% of the time, right? Anything below this absolute threshold is considered subliminal, right? So subliminal meaning like under our own recognition, right? The sound might be there, but we aren't recognizing it. So absolute threshold is the minimum level of intensity. So this is going from nothing to something. When do we go from nothing to something? I'll reference that again because that's in contrast to difference threshold, which we'll look at in a second. So with that said, signal detection theory is when absolute thresholds are not necessarily absolute, right? Signal detection theory refers to whether or not we detect a stimulus, especially amidst background noise. If you guys remember back to like we were in the sleep unit, we talked about the cocktail party effect and how we're able to localize like conversation. Even in a really loud environment, we're able to pick out one thing to listen for, right? That's that cocktail party effect. But the signal detection theory is related to that in the sense that it's referring to the fact, can we detect a stimulus or not? This depends not just on the intensity of the stimulus, but on psychological factors such as person's experience, expectations, motivations, and alertness, right? A lot of times people say that I have like really good hearing, or I'm really able to like pick up on extraneous conversations, like while I'm having a conversation with my husband at a restaurant, which has been a while, right? And I can hear what other people are talking about. I attribute that to the fact that I'm a teacher. I'm doing that all the time. I'm listening to 14 different things. 90% of them I wish I didn't hear. But based on my experience as a teacher and being in that environment, I'm able to be better at this signal detection theory. One example is parents of newborns being able to detect a faint baby's cry that others would not be able to pick out from the background noise. So myself, not having children yet, right, I'd not be as quick to pick out a baby crying in like a big party setting at a restaurant, whereas somebody who is a parent of a newborn would be very quick to perceive that. So that's your signal detection theory. So when we're talking about subliminal detection, right, we have our understanding of absolute threshold when we go from 0 to something. Signal detection theory is the thought process about whether we can or cannot detect a stimulus, specifically in background noise. And now we're going to look at like what our perception is below that absolute threshold. I referenced subliminal on that previous slide, but here we're looking at anything below our threshold, being able to consciously detect a stimulus, right? Research has been done, and it tells us that we can sense something without being aware of it. And it also tells us that we can be briefly primed but not enduringly influenced by subliminal stimuli. So the research component of this, the experiment that was done, if you look on the right side here, where there's these two images, basically what happened, people were sitting in front of a screen, right, and they were flashed the top photo, right, that had just like neutral colored dots on the right side and a nude picture on the left side. They were flashed it in such a short like little amount of time that they wouldn't have been able to tell you what they saw or if they saw anything. But once the second screen came up of all these colorful pictures, people across the board looked at the left side of the screen longer. And that's because that subliminal detection of a nude picture made them drawn to that side of the screen, even though they're the same image, right? So that gives us insight into what subliminal messaging does. You guys have all heard of CDs or albums that like if you play them backwards, they tell like the Illuminati's story and they're trying to get you to sign the devil's book or like whatever. Subliminal messaging and advertising. There's a bunch of examples. Feel free to look them up on the internet because they're actually pretty interesting. But they can prime our choices like immediately following that subliminal messaging, but like it's very short lasting. So with them, we're going to shift our attention then to difference threshold. So I referenced absolute threshold is going from 0 to something. The just noticeable difference, or that difference threshold, is referring to a minimum difference in color, pitch, temperature, weight for a person to be able to detect the difference, right? So our difference threshold is when can we tell the difference between something. So in that sound test, right, that you have to sit in the nurse's office, right, you hear a noise, right, and then you can perceive that it gets louder or it gets quieter, right? That's our difference threshold, right? Weber, that's how you say it, Weber's law refers to the principle that for two stimuli to be perceived as different, they must differ by a constant minimum percentage and not a constant amount, right? You don't really need to know the intricate, ideas behind this. You don't need to be able to calculate it by any means, but just understand that when we're looking at difference threshold from person to person, from individual to individual, being able to perceive a difference is always going to be a difference by a constant percentage, right? So just kind of keep that in mind. So when we're talking about difference threshold, we're really thinking about this idea that we're able to perceive a difference in color, pitch, weight, or temperature. Can you notice on the screen here that around difference threshold, the color of white is just 1% darker? Can you notice that? I'll show you again. There's the original. Look around difference threshold. There's the darker square. Now, some of you might not be able to perceive that. That's okay. That means your perception or your difference threshold for color pigments is just different than somebody who can see it. So again, here around difference threshold, the white square is just 1% darker. So looking at absolute threshold and just noticeable difference, again, I said absolute threshold, something to nothing, right? 0 to something, right? When you can't hear anything to when that first time you can hear the beep, whereas the just noticeable difference, right? Can you tell the difference between these two colors perceived here, right? Again, you might not be able to. There is a difference. It's 1% of a shade darker. So just kind of referencing that. But absolute threshold versus just noticeable difference. We are going to watch a quick video that gives you insight into what exactly that difference is so that you can remember absolute versus difference threshold.
Well, here I am in my car, and I'm going to use my car stereo here to do a demonstration of absolute threshold, difference threshold, and Weber's law. Alright, there's a song playing, and I'm going to turn it up very slowly. Right now it's on 0, volume is 0. I'm going to turn it up very slowly, and the second you hear it, it will have crossed your absolute threshold. Now the volume's on 1. Do you hear it? 2. If you hear it now, it just crossed your absolute threshold. It's on 3. Now you probably hear it. It's at 4. It probably crossed your absolute threshold. 5, 6, 7. I hope you can hear it by now. It's probably crossed your absolute threshold. So the second that you can hear something, or see something, or feel something, the second that you detect it, the second it goes from nothing to something, it crosses your absolute threshold. Difference threshold is when you can detect a difference in a stimulus. So if I crank this up to like 20, it's pretty loud. If I change it 1, it's hard to tell a difference. Can you tell the difference between 20 and 10? I'm sure you can. You can probably tell the difference between 20 and 10. If you can tell a difference when I turn down the volume, it's crossed your difference threshold. Now, it's easier to tell a difference between something like 5 and 10 right? 5 to 10. You can tell the difference. But I'm going to turn it all the way up to 25 and see if you can tell the difference between 25 and 20. Or how about 30 and 25? Harder to tell the difference when a stimulus is really loud or really bright in terms of light or really smelly in terms of smell. Well, here in terms of sound, it's harder to tell the difference between 20 or 30 and 35 than it is to tell the difference between like 10 and 15. Easy, right? Now 30 to 35. So that's Weber's law. Weber's law shows that it's easier to tell the difference between a low stimulus, and it's harder to detect a change in a really loud stimulus. There you go.
So one thing to think about as we're talking about perception and like our ability to perceive different stimulus is this idea of sensory adaptation. Hopefully that video kind of showed you the difference between absolute, going from 0 to something, and difference threshold, the change between two stimuluses. Sensory adaptation is the idea that we're able to detect novelty in our surroundings. Our senses tune out constant stimulus, right? So if you have there's a ringing, I know my classroom had this fan that made a weird noise, and you never really noticed it unless somebody pointed it out, right? And then you're like, oh God, that's so annoying, I wish I didn't think about it, right? That's sensory adaptation. We don't notice this visually all that often because normally our eyes are constantly moving. We don't really adapt to stuff in our visual field unless we're talking about sensory adaptation as it pertains to when it's dark out versus when it's light out. Have you ever noticed that if it's dark out, right away you can't really see much, but as 2-3 minutes into hanging out in the dark, I don't know why you're hanging out in the dark, but if you are, your eyes begin to adjust. That's sensory adaptation. Same thing when you walk outside and it's super sunny and you've been in school all day and all of a sudden you're like, oh my gosh, I can't see anything, I'm blind, right? And then your eyes adjust. We'll talk about what exactly the biology of that is, but that's sensory adaptation. Couple other examples, right? If you get a rock in your shoe, it bothers you and then you forget about it. The ticking of a clock is more difficult to sense after a while. When you're first sitting in a quiet room and it's there, you hear it pretty clearly and it's very annoying, but as you hang out, it starts to go away and you forget about it. So we're going to watch one optical illusion, and that's an example.
Other kinds of cells can also get overstimulated, and that's what's going on with a spiral that's sometimes called the waterfall illusion or the motion after effect. Stare at the very center of this spiral and try not to blink. Keep your eyes locked on the spot. You're getting sleepier, very sleepy. Getting sleep. Okay, that's a different thing. All right, now, how do I look? A little bloated maybe? A little spinny? The motion after effect is the motion version of the magenta rectangle from before. Your eyes have special cells that detect movement and rotation in different directions. They are really important to help you navigate the world, but they can get overused just like your color cones. Scientists think that's what happens when you watch the spiral. The cells that detect rotation in that direction fire constantly, while the ones for the rotation in the other direction aren't doing much at all. The firing cells were exhausted by the time I showed back up on the screen, so they probably couldn't respond well enough to match their neighbors and tell your brain that I wasn't rotating. So your brain assumed I started rotating the opposite way the spiral was, which is why I seemed like I was spinning in the opposite direction of the spiral. It's called the waterfall illusion because rocks can start to look like they're moving up into the sky after you've been staring at a waterfall for long enough.
Of sensory adaptation, it's the motion after effect, and it's actually just a clip from this video, so don't worry, you're not watching a 9-minute video here, but it's pretty interesting. Right, so this is just like one example, and it's not like specifically pertaining to sensory adaptation, but it is, in a sense, showing us that like our brain adjusts to that rotation, our brain adjusts to that movement, so that when we see something standing still, our kind of top-down processing continues to see the screen turning in a circle, right? That's our example of sensory adaptation here. So we're going to move on and look at perceptual sets, look at some optical illusions here moving forward, and then we're going to talk about how attention impacts our sensations and our perceptions, which is a pretty fun little bit. So here we go. Perceptual set is what we expect to see, and that influences what we actually see. So perceptual set is an example of top-down processing, right? So here, looking at these two images, right, what do you see? What do you expect to see? Right on this left one, do you see the Loch Ness Monster, or do you see a tree branch? Right, and the one on the right, do you see UFOs, or do you see clouds? Right? And so perceptual set is kind of what we're primed to expect to see, influencing what we do in fact see, right? Like on this right one, that's not what our general concept of a cloud is, right? A cloud is big and fluffy and round. This is kind of like circular and spinny, right? And so we perceive these to be more like flying saucers than we do clouds because of our expectation of what a cloud should look like, and that's not it, right? Here's another one. Your perceptual set can be primed. You see the word old woman, and you look at the screen and you see an old woman, right? If you look at the right side where it says young woman, you'll pretty quickly see the young woman, right? Whereas if I were to put this up on the screen without any words, it's really difficult to kind of jump back and forth, right? Once you see it, you see it. But that priming, right, again, if the word old woman is up there, that's what your brain is going to look for. Whereas if I say young woman, again, that's what your brain is going to be looking for. So here's another example of perceptual set, specifically how context affects our perception. Looking at these two images, which center dot looks larger, right? Most people would say that the center dot on the right looks larger. You're primed right now to be like, ooh, what's the trick here, right? What is this optical illusion? And you might have been able to see that they're actually, in fact, the same size. But the context within a small dot surrounded by big dots, right? That dot looks smaller than the dot surrounded by little dots, right? Our brain puts into context what we are seeing, and we're primed to think, okay, that's a bigger dot because look at the smaller dots surrounding it, right? Again, some of these start to get tricky as we've worked through them a bunch because, again, your brain is primed to be like, ooh, I know there's a trick here. What am I looking for? Whereas if you were to just look at it out of the blue, you maybe wouldn't have that same kind of processing. So I want you to do a quick spelling test, okay? I would like you to write, you're going to write 3 sets of words, okay? And try and spell them as properly as you can, right? First word is double. Double. The second word I want you to write is pair. The third word I want you to write is apple. apple. The fourth word, pear. The fifth word I want you to write is payee. Payee. And then the last word, the sixth word I want you to write is pear. All right, this is another example of context. What I am looking for, I'm going to write this. I don't know how good it's going to be, right? Double. You know how to spell double, D-O-U-B-L-E. And the second word is pair. How many of you wrote P-A-I-R? Because you were primed to think double, two, pair, two. The next word was apple. And then I said payer, pair. I'm looking for the word payor, pair, right? And that's not to be confused with payee. That might have been a tricky one. And then the last word was pair, right? So there are obviously multiple ways to write pair. Pair as in like the fruit, pair as in like two things, and pair as in like somebody who is doing the paying. But because of the context and because you were primed, right, with words before, double would make you think two things. Apple might make you think like a fruit, pear. And payee might make you think like, oh, payer, payee and payer. But that wasn't exactly what I was looking for. Again, just a little trick, context. Gotcha. No, we just talked about that. Sorry, I messed it up. So here we go. We're going to talk about emotion just real quick and then look at attention. So effects of emotion, physical state, and motivation on perceptions. We have done experiments to find that destinations seem further away when you're tired. A target looks further away when the crossbow is heavier. A hill looks steeper when the heavy backpack or a sad music or when walking alone, right? Something you desire always looks closer. So like our psychological inclinations and our own perceptions do genuinely change what we are envisioning within the world. So if our backpack's really heavy and they tell us to run to some place that we can see, we perceive that to be further away than if we don't have a backpack on. And that's just kind of based on our psychological putting all of these together. So we're going to shift our attention to attention. Woohoo! Actually, this is very fun. This is like one of my favorite things in psychology. So here we go. We're going to look at divided attention and the Stroop effect. We're going to talk about inattentional blindness and change blindness and how these all relate to our understanding of perception. So the first thing is divided attention. Divided attention occurs when mental focus is on multiple tasks or ideas at once. This is also known as multitasking, and individuals do this all the time. You are probably doing it right now. You're listening to my lecture, maybe taking notes, maybe like checking your Instagram or whatever. But research has been done, and it has been proven that multitasking, nobody is good at it. You might be like, I'm a brilliant multitasker. They've shown that women are actually better than men at multitasking. They perform all the tasks better that they're doing at the same time. But they are still performing at a lesser level than they would if they were focusing on just one or the other. So you might think you're doing an okay job at multitasking, but research has shown time and time again that we as human beings, our brains are not good at this action. We can't multitask. And so what we're going to look at is this idea of divided attention, and the Stroop effect and the Stroop test is a fun little way to
Hello everyone. That test was tough, huh? I struggled a lot with it, especially round 4. If you want to learn more about the Stroop test and the Stroop effect, check out the video below. It's super interesting to see how your brain behaves during this task, and I had a lot of fun making this video. Thanks for watching, and I'll see you next time.
Kind of do that. It's asking you to look and perceive two different things and come up with a response that wouldn't be what you would normally look at. So I'm going to let you kind of take this without giving you any more information, and then we'll talk about how it relates to divided attention here in a sec. So the Stroop effect, hopefully that was kind of fun, but again, this is dividing your attention. It's asking you to not only perceive the color and read the word, but then you have to say the color of the word when your brain has been, like, since kindergarten, so conditioned to read words, not perceive their color. So this is an example of how divided attention, like, are you able to do it? Yes. Are you able to do it as well when you're looking for two things? No, right? The next one we're going to look at is inattentional blindness. And I'm really going to let this introduce itself. So we'll watch this video. I want you to really focus hard on what the instructions of the video are and try to make sure that you are keeping up with counting and figuring out what your job is, okay?
This is a test of selective attention. Count how many times the players wearing white pass the basketball. How many passes did you count? The correct answer is 15 passes. But did you see the gorilla? This video is from research by Daniel Simons and Christopher Chabris and is copyrighted. It is available for use in talks, training, and teaching on DVDs from VisCog Productions. Learn more at theinvisiblegorilla.com.
This one's fun. How many of you, I mean, if you've seen it before, or if you've seen something like it before, you probably knew what to look for. But for those of you who are really focused on just counting those basketball passes, and they were like, there were 15 passes, and you were like, yes, I win. And then all of a sudden they're like, but did you see the dancing gorilla? And you're like, wait, what? That's inattentional blindness. When you focus really hard on one thing, right, such as the actions of a main character in a film, you might not notice unexpected things entering your visual field, right? One of the primary reasons that we fail to notice things like obvious bloopers in movies, for example, is psychological phenomenon known as inattentional blindness. So, like, if you've ever seen the shots in movies where, like, from the front, I saw one just the other day on TikTok from Gossip Girl, when Serena, who's played by Blake Lively, is like looking all fresh and fancy in her little dress, stands up and is like talking to somebody, but then the attention shifts to the other character and the screen films back and you see she's like wearing sweatpants like 1 second and not sweatpants the next. It's pretty funny, right? Another example is if any of you are Game of Thrones watchers, at one point in the film, or at one point in the series, Khaleesi, or the blonde girl down in the front, had a Starbucks coffee cup, and the internet went crazy, but like nobody really I mean, I didn't notice it when I watched it because I was so focused on the conversation going on in the left of the screen. That's inattentional blindness. And with that, then, we have one more concept as it pertains to attention to look at, and that is change blindness.
Clearly, somebody in this room murdered Lord Smythe, who, at precisely 3:34 this afternoon, was brutally bludgeoned to death with a blunt instrument. I want each of you to tell me your whereabouts at precisely the time that this dastardly deed took place.
I was polishing the brass in the master bedroom. I was buttering his lordship's scones below stairs, sir.
Why, I was planting my petunias in the potting shed.
Constable, arrest Lady Smythe.
But how did you know?
Madam, as any horticulturist will tell you, one does not plant petunias until May is out. Take her away.
Sorry, madam.
It's just a matter of observation. The real question is, how observant were you?
And action.
Clearly, somebody in this room murdered Lord Smythe, who, at precisely 3:34 this afternoon, was brutally bludgeoned to death with a blunt instrument. I want each of you to tell me your whereabouts at precisely the time that this dastardly deed took place.
I was polishing the brass in the master bedroom.
I was buttering his lordship's scones below stairs, sir.
Why, I was planting my petunias in the potting shed.
Constable, arrest Lady Smythe.
Did you get it? Did you see all those changes? Were you like, no way? Like, you're so focused on trying to figure out the crime, right, that you forget to like think about all of the little things that are going on in this particular video clip, right? Change blindness is a perceptual phenomenon that occurs when a change in a visual stimulus is introduced and the observer does not notice it. For example, observers often fail to notice major differences when introduced to an images when it flickers on and off, right? You're so focused on the flickering, you don't realize the changes that are taking place, right? Total characters, like human beings and their faces and what they look like changed in this whodunit clip. And yet many of us are so focused on what we're supposed to be focused on, like who killed whomever, right? Like we don't think about all of the other stuff. So change blindness, these are all examples of how perception and how our perception can fail us, right? Again, thinking about our divided attention and multitasking, inattentional blindness, and change blindness. So that's what I have for you in regards to our introduction to sensation and perception. So there you have it. This is one of my all-time favorite lectures, just because it's so interesting to think about how our brains actually work. And these optical illusions are just cool. They get our brain kind of going and thinking about things that we maybe wouldn't normally think about. So hopefully you enjoyed that. Like I said, intro to vision and perceptual cues tomorrow, and a scavenger hunt photo thing on Wednesday. Enjoy. Happy Monday.